Hello, everybody. So this is the second recording about this this sequence or recordings trying to get what is the use of a hidden Markov model here to assess similarity. Yeah. So in the first recording, what I address is basic idea of how we assess similarity between sequences, maybe amino acid sequences, or maybe also nucleotide. So in this second recording, what I'm going to discuss is pretty much how do I get the sequences, or at least some basic idea how to get it. Okay, sorry. So where it comes from the sequences, it depends pretty much on which question of interest do you have it, which research are you are trying to address. So I will start with a very basic example based on the results of an article. This article, the title you can see that is the role of the S100 protein family in rheumatoid arthritis. Yeah. So in this, well, if you are really interested, this is from January 2022. Is 3 years ago. And for sure, if you are interested in going and explore what is the idea behind, you can go and get the details. This is one image that you can find in this article where you are seeing the intersection between three circles pretty much. So in blue, you are seeing how is this circle representing the inflammation. In green, you are seeing how this circle is representing the proliferation, and it's something like in yellow, orange. You can see another circle representing rheumatoid arthritis. So, and the idea, this is some S100 proteins that sometimes they belong just to one circle. Sometimes, in this particular case, they belong to the three circles at the same time. Yeah. So here you can see a list of this family, S100, S100, and here we can see some elements. Right now, what I'm going to do is to focus on one of them, in particular in this one that it says S100A4. Okay. And after that, I'm going to jump to the NCBI database. The NCBI is National Center for Biotechnology Information. Here you can find a link, a link, and you can jump straight forward to there. Yeah. So what I'm going to address here is exactly that. I'm going to look one of the proteins that is from this family, and I'm going to use this A4. That is the first one in this list. Yeah. And since I'm talking about protein, I'm going to open this menu here and see how I choose the one that says protein. Okay. After that, I can go and search. Depends on the internet, it depends on the time, how much it takes to get some results. In this particular case, I will add more filters. So I add these filters, this is the name of the protein and the database that I'm looking for. I'm going to add more details here. In particular, I would like to focus in this one, those are the results that contains information in this database that the name is the PDV. What is PDV is protein database. Yeah. So once I get this, I have more something. Since I add another condition, I get less results now. And for instance, here I can see, well, this is the name, this is the gene, and I can explore different things here. I'm going to my first record here that says S100A4 metastasis factor, chain B. I can go and access there. And when I access there, I can get the information about this information about where it was published. There is a reference, where the name of the author, where the name of the title, and how this protein was reported. In this particular case, since it is contained in the PDB, this is the source, that is a Homo sapiens, the method, how it was the information collected. and the resolution at the method is 3.1 angstroms. And for sure, since again, I'm trying to look for addressing the question, how I get the sequences, I'm going finally for this FASTA link where I can finally get the information on the protein. Yeah. So in this moment, you can see that this is the name, this is the something like the code to locate the this sequence, and here you can see the sequence of the amino acids properly. And here, when you are accessing the PDB, there may be different chains. This is chain B. Yeah. Now, if you want this to jump to your computer to download the information, you can here in send to in a file, you choose the format that is FASTA. There are different formats here. I'm going to choose this one that is FASTA. Yeah. And when I said create file, I get here in my computer the sequence.fasta. There it is. Yeah. When I open, I can see that this is the information that I have at sequence. I have my sequence of amino acid associated with this S184. That is a metastasis factor. That is the information that I was looking for. Okay. Questions about that? So this is pretty much how it works. And finally, our next step, it will be to start talking about BLAST. What is BLAST? And as you may see here in the next, to the right, in the menu to the right of the sequence of the amino acids, there is a particular option that says run BLAST. Yeah. And right now we are not going to run BLAST. If you are interested, you can go and run it. Before that, I would like to address what is exactly BLAST. Here in these slides, you can find something like a BLAST tutorial where you go and click that link. You can find this Science Body channel in YouTube. That is a very simple tutorial, short tutorial that is 12 minutes on how to use BLAST for finding and align DNA protein sequences, in this case that you are interested. Okay. I'm not going to run the BLAST. I'm going to discuss right now how it works BLAST and what is the main idea behind. Okay. What is BLAST? Well, BLAST stands for Basic Local Alignment Search Tool. Okay. This is what it means, this BLAST. And as you may see, this is an algorithm that helps you to find some sequences that are similar to the one that you are interested in explore. This one is an algorithm from 1990, so as you may see, there is no reason at all. Nevertheless, this is the first version. Along these years, there are different things that have been updated and optimized to get better results. Yeah, and that's exactly one of the things that we would like to discuss in these slides. So behind the BLAST, what it is a idea of try to follow some rules of similarities to understand if when you are comparing with another sequence, if these two sequences are similar or not. Okay, so and the strategy that BLAST follow, the name is the maximal segment pair. What is a maximal segment pair? Is something like a particular subregion or subset of the sequence that you would like to find a very high score because it's very similar to another segment in the original sequence. Well, I'm using the word score, assuming that you saw the first video. And if you remember, we discussed that there is some matrix, the scoring matrix that allow us to compute something like a score when we are comparing two sequences. Yeah, so this is an idea that we are going to elaborate a little more in this. So the idea of this maximal segment pair is at the very beginning to start with a very small one, and after that to start expanding or increasing this region, this segment, try to increase this score. And this is exactly what I want to right now to try to explain. So at the very beginning, you find something like a match that is very similar, and after that you start something like extending this region, this small region, and the boundaries of where we will start this segment pair or we will finish. At the very beginning, you don't know it. So when you start expanding, you are going to, or we expect to start increasing the score. And this is exactly what I want to try to explain right now, okay? So for instance, imagine that you have this, you are comparing these two sequences, and you have this short piece here. I'm going to write down exactly the same letters that you have it right to the left. L, F, and W. So I'm considering this bunch until here. Yeah, and down what you have it is an O, down to the L is a D, P, another P, E, G, B, A, and L. Okay, so at the very beginning, you are considering this segment. Okay, PQG, and you are comparing with this one. This is a segment pair. And we are not using this word yet, the maximal. You know? So we are looking for a segment. Right now we have a segment pair, and where it comes from, this idea of the segment pair is that you are considering this the specific region of the sequence, the PQG. And when you're comparing with the other sequence, you can find this PEG that is very similar. How do we know that is very similar, or how do we determine this? Is based on our score. So if you remember that last video, we have something like a, or I show you something like a matrix with some values. So it's in the moment that you are getting these values in common that you start adding values to the score. So at the very beginning, again, so what happened here in this first position? You are getting P, and when you're comparing with the other sequence, you are getting P again. Based on the matrix that I showed you last time, it means that here you are getting 7 points because you are getting P and P also in the next one. In the second position, in the first sequence that you have in the sequence of interest, I'm going to call this one that is the query. This is my sequence of interest. Okay, so I have in a queue, and as you can see, here we don't have a match. Yeah, so but we don't have a match doesn't mean that we are getting a negative value. So it depends on the value or the letter that we found in the other one. That is the subject sequence is the value of the score that we are assigning. So when you find Q and E together, we are assigning a 2. So it means that this is something that is increasing the score, not necessarily is a very high value that is increasing, but at the same time, what it means that it's something like a substitution, but is positive in the sense that increases our score. And finally, in the third position, we are getting another identity that is G with G. In this case, when you get G with G, the score is 6. So when you add these three values, something that you figure out very simple is the 15 that you have it here. Yep. Questions about that? So I'm going to discuss in some minutes, or maybe not in this video, in the next one, where it comes from, these values, 7, 2, and 6, that kind of things. Yeah. But right now, the idea is just to understand what is behind of the blast. So at the very beginning, we start with a segment pair. This one segment, this is a segment pair. And after that, I would like to start what? Is try to extend this segment to the left and to the right. Okay. I'm sorry. So in the moment that you extend to the left and to the right, what happened? Here you have what? Other match, P and P. Oh, nice. And here you have L and B. Okay. So to the 15 that we have it at the very beginning, just in the first three letters that contains the first segment. When you start expanding or extending this segment to the one position to the left, one position to the right, what happened? You get again set P and P. So again, you will have another 7. That is the one that we have it here. And to the right, you have an L with a B. This one is a combination. Again, the L is being substituted by the V, and this is a substitution that, again, is a positive value also. What does that mean? It means that if you extend one location or one space to the left and one space to the right, the scoring is increasing. Hmm? Does that make sense? So it's increasing, and it's increasing to 23. Questions about that? No? Is the 7 that the P and the P, and 1 that you have it here. So you have 15 at the very beginning, 7 is 22, and 1, 23. And after that, you would like to continue doing the same. So if you extend one position more to the left and one position more to the right, this is the moment that the score start decreasing. So if you get the R and the D, what happened? This is a combination that produces a negative value. This is a combination that produces a negative value. The same for F and V, produce a negative value also. What does it mean? That is, in this process of extending to the left and to the right, there is a moment that the score start decreasing. Yeah. So in that moment we stop. What does it means here is I find something that the name is a high scoring segment. Yeah. It's a high scoring segment. Yeah. So it's a segment. I start extending, so I will reach a bigger one. And here I have something like a trying to determine the boundaries of this segment pair. Okay. This is the idea behind the blast, the very beginning. This is the way how the algorithm works. So it's start by selecting something like a very small piece. That is the one that I show you here. And based on that, I start assessing if there is similar to the subject sequence. Yeah, and once we find a segment pair that is reasonable, we start trying to extend it. What does it mean to be reasonable? This is exactly what I'm going to try to discuss next in the next slide. So in this one, what I wanted is, okay, this one, well, first, before to jump this, remember that this maximum segment pair, what the idea is to provide something like a local similarity measure. Yeah. So this the idea is just to comparing something like a very short and small maybe piece of the sequence, and they're trying to assess if this piece is similar to the sequence that we are comparing to. Okay, and what is trying BLAST to do is to assess the similarity, but in a very fast way. Yeah. So as you can imagine, if the algorithm trying to check all these very small pieces, it may takes a very long time. So what is BLAST trying to do uh, is pretty much to find these short pieces that that we describe as a pair. Blast can find this kind of pair very fast if you set something like a cutoff. So in the moment that you have something like a cutoff, Blast can look for all the segment pairs, like the one that I discussed in the previous slide. That is getting some scores above this cutoff that you decide. Yeah. This is not to go and test all the possibilities, because testing all the possibilities takes a lot of time. Of course, you can do that if you have enough time. Yeah. If you don't have enough time, you would like to optimize the search. And for that, Blast, what it's trying to do is to, okay, I'm going to set a cutoff, and based on that cutoff, I'm going to look for these pairs, assuming that, or not assuming, recognizing the one that are above or get a score above this particular cutoff. And we are going to discuss how to choose this cutoff in a way that we get significant results. Okay. So let's see. In that moment, not right now, I'm going to start talking about the idea behind Blast. In Blast, you have something like what I designed has the three letters, in this case, of the original sequence, that the name is the query. Plus, understand that as a word. Why? Because the strategy that we follow here is something like a language algorithm. Uh, so in this particular case, if you would like to understand some terminology, you can go here to the Blast glossary. And in the Blast glossary, here, give me a second. I lost. Okay. In the Blast glossary, you can go here and find some information about what is the meaning of each case. In this particular case, this figure that I'm showing you here is in the Blast particular, uh, in the Blast glossary. You go for the word Blast, and you can find the same image and some explanation as the one that I'm going to try to explain right now. Okay, so in this particular case, you have the query, that is the full sequence, and you are using a query word. In this particular case, you choose that the length of the word is 3. Okay, this is something like a parameter. And right now we are going to talk about these values. So how many letters are here in this word? In this case, at this same 3. Or what is the cutoff that I mentioned previously, that here I'm going to use 13. Those are parameters of the algorithm. Okay, so what happened? How we expect if we change the parameters? Of course, we can have some different results in our search. So right now the idea is to find, okay, to understand given some parameters, our decision of the parameters will be understood as based on time spent in the search. After that, the potential error that we have it. What does it mean? It means that since we are setting some parameters, it may be that we made some mistakes and we don't recognize some sequences that really are similar. Yeah. So this is the price to pay based on some parameters, and we're going to discuss why we can trust in tools, or what is the pretty much the selection that works, or what is the pretty much how we understand this time spent and potential error based on the parameters that we choose it. Okay, we're going to discuss that. But right now, I would like to explain how it works, the algorithm, before to jump to this choice of the parameters. So here I have this this image that I'm considering, okay, right now I'm considering a word that contains just three, oh, I'm sorry, that contains just three letters. Okay, so I would like to work around this word. And what it means around this word, it means a neighborhood of the words. So I'm considering, again, some words or some combinations of three letters that are very similar to this one. So if the original word is PQG, that's the one that I have it here, PQG, uh, I think I want to write down, okay, the original word is Fury. It is B, Q, G. Okay, and now I'm going to write down some neighbors words. What does it mean? Or I'm going to use the word synonym. Okay, of the same that I'm saying here, the neighborhood words. Can be words that, okay, instead of having PQG, I'm changing by something else. So if I have an identity in my subject sequence, I have PQG in the query and PQG in the in the subject. This is the score that I get at 18. Okay. If I find exactly the same letters, I will have the 18 as my score. Okay. So this is what I'm going to try to understand right now is, okay, if I change, this is the best situation that I can have it. Okay, I have 18, and is when I get exactly the same word. If I have a letter that is different, among the three, just one letter that is different. So for instance, if I start as in the next letter, in the next combination that I'm showing you, that is PEG, is the first scenario. The second one, PEG. So right now, I have two identities here. That is P and G. And the only one that is not equal is E. So I compute again the score, and the score, as you may see, is 15. So here the score is 15. Here the score was 18. So these synonyms words or these neighborhood words allows me to find something like a segment pair that um, that with a segment pair which I can compute very, very fast, this this score, this is short score. Okay, so when I'm considering more combinations, okay, I imagine that I keep fix the P and the G, and I change just the middle letter. So as a third combination, I'm going to use P. I'm going to jump to this one, K and G. Okay, so again, the only letter that is changing is this one. If I compute the score, I will see that the score is 14. So you can see that the score here can be decreasing, and at some point, if I continue considering other letters or other neighborhood words, I can find some words that now are producing something like a score that is very, very low. or not necessarily very low, but for sure it's not that high as the one that I get it. For instance, if I get this word, if I compute the score, PQA, the only one that I have different now is the third one. So now I'm matching the first two letters, and this is the third letter, the one that is not the same. If I compute the score is 12. This score is not that high. Yeah. So as you may see, based on this cutoff, that is 13, here I'm seeing some words that are not really high scoring. Okay. So in that way, if I don't get in a high scoring um, word here, I can say, okay, no, since in this bunch, I cannot find something like three letters that generate a score that is greater than this threshold that I have it here, I would put it out this sequence. Yeah. So in that way, Blast tried to make something like a filter, a very fast filter in the sense that, okay, if these segment pairs that I'm comparing are not producing a subscore that is sufficiently high or is higher than 13, higher or equal than 13 in this case, I won't consider this full sequence as something that can be similar. Okay, this is the way that Blast starts doing a filtering of these sequences instead of comparing the full sequence and to see how similar it is. Yeah. So by comparing these subwords, Blast can improve the time of of these go and look in a database and take some similar sequences. Okay, let's see. And some technical problems here. Give me a second. I'm coming. Okay, back again. So right now, I'm going to try to start discussing some concepts that we can find in this article that is using Blast to teach evolutionary concepts. And this is something like will allow us to understand not just when you are computing this score, if the score that we're getting is something that we will say as it is statistical significant. But before to jump to that, I would like to highlight some things. So the first thing is, okay, when you are computing these maximal segment pairs and you're looking for a database of thousands of sequences, in general, there is just a few of the sequences that are homologous to the query that you are looking for. Yeah, so go and look for these thousands of sequences. For sure, we would like to have something like a way to go and explore in a very fast, to scan in a very fast way. Yeah, before to spend a lot of time. Okay, so in this case, Blast what I do is to identify only those sequences with maximal segment pairs over some cutoff, and I'm going to use the word the letter S here. And the nice part here is that we have math results and statistical result that allows you to understand how this scanning or this filtering that Blast is applying, uh, how how it's affecting our search. Yeah, and this is exactly the point um of this algorithm that we continue using after 30 years, because these mathematical results are based on this element or this maximum segment pair concept that I tried to explain previously. So the idea is how these searches can be accelerated. And again, I'm going to look very, very fast now based on the word that I mentioned previously. But right now I'm going to compute some scores, or at least I will show you some results based on the substitution matrix that we have it. So in this particular case, I choose again a word of 3 letters. That is, the first thing of the blast is go and look for a subsequence of the original sequence. Let's consider this one that is marked here in red. SWVSQ. This is the one that we have it here. After that, you select the length of the word. Mentioned in the previous one that the length of the word can be 3. And here I'm considering splitting this fragment in words of 3. Yeah, so it is WV, WVS, WVS, VSQ, SQA, and you continue that way until you finish. Yeah. So for the first one, SWV, okay, you start considering some synonyms or some neighborhood words. So SWV, that is exactly the same. When you find an S with an S, so you are going to here look for an S and an S. S and an S, what happened? You have a 4 here. This is the 4 that comes from. Okay. Is that clear for you? Let's see. So this one is the S with an S. Yeah, that we have it here. After that, you compare the W with the W. The W with the W give you an 11. And finally, V with the V. V with the V. Where's the V with the V? The V with the V is the last one. Yeah, that is this 4 that you have it here. Let me see if I get it. Oh, these 4 different 4. Okay. So this is the way that you get exactly this 19 that you have it here. So if you consider another word that is SWI, I'm going to mark this in red. Okay, this one SWI. The SW is exactly the same, 411, but now what happens if you compute the V that is in the last one with the I? The V with the I will be 3. Is the 3 that you have it here. Okay. So this is the way that you try to compute the score based on what? On the substitution matrix, on the scoring matrix that we discussed last time. Here, the threshold that is set is t equals 11, equal 11. In the previous one was t equal 13. Yeah. So again, those are parameters that, based on the choice, we will have some errors in the search, and we would like to understand those errors. Okay. Questions about that? Okay. So the idea is BLAST try to minimize the time spent on sequence regions whose similarity with the query has little chance of exceeding some score. Okay. So if you start doing this analysis of the words and these segment pairs, so if you're getting a very slow score, BLAST try to discriminate some sequences based on that. If the score that you're getting is not that very high, so you would like to think, okay, no, maybe this sequence is not really, really similar. Okay. And scanning through a sequences, one can determine quickly whether it contains a word of length W, that we use 3 in this case, that can pair with the query sequence to produce a word pair with a score greater or equal at some threshold. Okay. Any such sheet is standard. As I show you, you move it one space to the left and one space to the right until the score stop increasing. Yeah. This is exactly what we try to do. Yeah. So After you analyze this one, you start extending to the left, extending to the right, and at some point, if the score starts decreasing, it means that you stop there. Okay. Okay. So this is something like an alignment that is obtained after you run the blast. So here I'm using a query, and then I'm saying here, okay, it starts in 1, and the subject, and that is the sequence where you are comparing. As you may see, it starts in the position 393. So because remember that it's a local alignment when we're doing here. Since it's a local alignment, doesn't mean that no, it means that the sequence is not necessarily started at the very beginning. Okay, so in this case, this is some information that you can get after getting the blast. Remember that you have a link here to go and look in the tutorial. And when you're comparing here, you may see that when you're having a letter in the middle, it means that you have an identity. Yes, so F and F, A and A. Here is some basic result about this. These gaps is these dashes that we are here. We have 16, is 8%. Positives, what it means that when you get a letter and you compare in the query and you compare with the letter in the subject, and you go and look for the scoring matrix, the value that you get it is positive. That's what it means. So you have 95 identities. What it means that the letter in the query is exactly the same letter than the subject. Yeah, identities is what it means. Nevertheless, there are some others that are not the same. Nevertheless, in the end, you are getting a positive score. Yeah. So sometimes you will have different letters. You will have penalization. It means that you are adding a negative value. And the expect e-value or the e-value will be e to the minus 44, 42. This is exactly the measure that we are going to use to see if we can trust in this result of similarity. So based on this, we can try to, we understand that we have two sequences that are similar, okay? So some remarks here, if the threshold that you choose is at the t, if you start decreasing this threshold, for sure, you're getting more segment pairs. And if you're getting more segment pairs, it's more likely that you're getting uh, um, a higher score when you compare this. What happens if you reduce this value of t? For sure, it means that you're going to spend more time because the first filter is allows to pass a lot of sequences in the moment that you start decreasing the t value. And finally, there are some random simulations that allows you to understand how to select the t that balance these considerations. Yeah. So behind this idea, remember that is to choose a t that allows us to scan in a very fast and simple way if the sequences that we would like to compare is kind of similar at a first sight. Yeah. And after that, if it is kind of similar at a first sight, you said, okay, no, this one, I think that we reach our goal. I would like to, I'm going to scan it fully. Or if from a first sight, I can say, no, I don't think you will reach it. You discard that option instead of scanning completely. Yeah, this is the idea of this T. Yeah. And as I mentioned, if you put a T very, very small, you have more and more sequences to um, to compare fully or completely. And if you start increasing the T, you are going to discard more and more and more sequences. Yeah. And at the end, this idea is which allow us to understand that choosing some parameters will have some consequences in results of the search. And now, as I mentioned, the last bullet, based on some simulations, we can understand what is the threshold, what is the value of T that allow us to get a balance between these two remarks. Yeah. The tool that we're going to use it to understand is this heuristic way to compare sequences is really, really significant. or is something that we can trust? Is the e-value properly? Is the one that I mentioned previously. And the e-value will allow us to understand if the similarity that we find between those two sequences are statistical significant. Before to jump to this, well, this part, I'm going to address this part in the next video, in a third video. I would like to stop here because I'm not really sure if what I explained to you was very clear. So I'm going to stop this video here. I'm going to share with you, and based on your feedback, I will try to get back to details of this video or to continue with the next one. So thank you very much.